Okay, the last part of Unit 1516 is solving inequalities, which is very similar to what we did in Unit 5, where we are going to make an interval table to solve it. So remember that when we are asked to solve an inequality, we are just asking where is the graph above the x-axis and where is the graph below the x-axis. So we can find that information just from a table. We don't even need to graph it. So the important parts of the interval table are the x-intercepts, because that's where the graph sits on the x-axis, and so it will change from going above to below or vice versa. The other important feature is the vertical asymptotes, because again, that's a point where the graph is probably going to change from being above or below or vice versa. Okay? So in a rational function, the numerator is what determines the x-intercepts, and the denominator is what determines the vertical asymptotes. So for example, if we want to solve the rational inequality, and we don't really want to graph it, we are first going to find the x-intercepts, which is determined by the numerator. Because if y equals 0 and I cross multiply, that would eliminate the denominator. So the numerator, I solve for x, and that's my x-intercept. The denominator determines my vertical asymptote, because I know the denominator cannot be 0. So we take the denominator, solve, and that will be my vertical asymptote. So this is my vertical asymptote, and this is my x-intercept. So those are the intervals I want to check. So if I put them in order in my table, so table similar to what we did in 5, I want to know what happens to the left of -2, what's happening between -2 and 1, and what's happening to the right of 1. So that's saying what's happening to the left of this vertical asymptote. This is where the vertical asymptote occurs. This is where the x-intercept occurs. And then I put my numerator, which is x minus 1. I put my denominator, which is x plus 2. And combined, that gives me the function f of x. In the guide, they do separate numerator and denominator. You don't have to do that. You can if you want, but so what they do is find the sign in the numerator, the sign in the denominator, and then just put them together. But you can just do it all at once. So I'm finding a value that is less than -2, so I'll just use -3, which gives me a negative result, and then combined a positive result. That tells me that when x is less than -2, the function is above the x-axis. And I'll pick a number between -2 and 1, let's say 0. So I get a negative result. That tells me the graph is now below the x-axis, and then I'll pick a number bigger. And that tells me to the right of 1, it's above the x-axis. So the question is asking, always be careful whether they're asking less than or greater than 0. This says less than 0, which means where is it negative? And this is the interval over which it's negative. So x is negative between -2 and 1. So I don't need to graph the function. I just need to solve by looking at where it's positive or negative. So likewise this one, the numerator would give me my x-intercept. So that is 2. My denominator, I have 2 vertical asymptotes, one at -3, and then one at 0, at 1, sorry. So those are the 3 values that are important. The vertical asymptotes here and here, and then the x-intercept here. So I want to know what's happening to the left of this, what's happening in between, and then what's happening to the right. And so those are the values I'm going to include in my interval table. So to the left of -3, between -3 and 1, between 1 and 2, and 2 and infinity. And then I put my numerator, which is x minus 2, my denominator, which is x minus 1. And then we'll just pick some test values in those intervals. So I'll pick negative 4, negative, negative. I'll pick 0. I'll pick 1.5. And I'll pick 3. And then the question, same as the last one, where is it less than 0? So it is less than 0 here and here. So this is my solution. So less than negative 3 and between 1 and 2. Let's see. Okay, so let's do this one. Should we do this one? No, we'll skip that one. So let's do this one. Okay, because this one has some different issues. So in order to, so just take a note in this one, maybe we'll do this one. Make sure that it's factored first. So I'm going to factor the numerator. So some of them will require factoring. They won't be in factored form. The denominator's a difference of squares. Okay, so my x-intercepts are at negative 2 and 1, negative 1. That's a plus. And then my vertical asymptotes are at 4 and negative 4. So if you want to put them on a number line, just to make sure you get them in increasing order, and that will tell you what intervals to check. So from negative infinity to negative 4, negative 4 to negative 2, negative 2 to negative 1. Need a little bit of room here. And negative 1 to 4, and 4 to infinity. So this one has quite a few intervals to check. Okay, so you might need a bit of room for that. So in the numerator, we have x plus 2, x plus 1. In the denominator, and then the result. So less than negative 4, I'll pick negative 5. Negative, 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 negative. Results in a positive. Between negative 4 and negative 2, I'll pick negative 3. Negative, 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 positive. So that's negative. I'll pick negative 1.5, positive, negative, negative, positive. So positive. And I'll pick, I don't know, 0. And the last one. Okay, so where is the function less than 0 in this interval and in this interval? So that one required some factoring between negative 4 and negative 2, and between negative 1 and 4. Okay. So this one also requires some factoring. So in the numerator, we have a common x. In the denominator, we have a difference of squares. Now, this one is a little interesting because we have a factor that reduces. So what we are actually going to solve is x and x minus 2. And I'll show you what happens once I graph this. So we don't need to include the x plus 2. We are just going to do the interval table with x over x minus 2. So the x-intercept is 0 based on the numerator, and the vertical asymptote is 2 based on the denominator. And I'm going to do my interval table. And then I'll graph it on Desmos just to show you what's happening. So we want to negative infinity to 0, 0 to 2, and then greater than 2. Okay, so let's pick a number less than 0. I'll pick negative 1. And then we'll pick a number between 0 and 2, so I'll pick 1. And then greater. So my solution is, where is it greater than 0? It's greater than 0 at less than 0 and greater than 2. But what about this factor that was reduced? So when a factor is reduced, because normally when I look at this, I would expect it to have 2 vertical asymptotes. So when a factor is reduced, I would, when I graph this, I would expect to have a vertical asymptote at 2 and -2. But when that vertical asymptote gets reduced, the vertical asymptote is replaced with what we call a hole in the graph. So I'm just going to type this into Desmos just to show you. I think I need brackets here. Okay, divided by x. So I'm not going to put it in factored form. I'm just going to put it in the original form. Okay, so here is the graph. Okay, so you can see that there are not 2 vertical asymptotes. There's only 1. And it occurs here at x equals 2. Okay, the one that was at x minus 2 that we factored and reduced is gone. All right, so this one that we reduced at x plus 2, so that creates a vertical asymptote at x minus 2, that's gone. It's not on the graph, as you can see. But if I take my mouse and I go to x minus 2, so if I get exactly on x minus 2, you will see, if I can get this to stay, you will see here that it says at x minus 2, it is undefined. Well, that's because it's a restriction, first of all, because those vertical asymptotes are where x cannot be. So you can see that that vertical asymptote that was normally expected to be at -2 is now just a hole. So you can see that it's not filled in when I click on it. It's an open circle. And that's what happens when you have a factor that is reduced. So this is what my graph looks like. So I'll just put it here. So we had a vertical asymptote at 2. My horizontal asymptote, if I were drawing this, the degrees are the same, so it would be the leading coefficient, so it would be at 1. So my horizontal asymptote would be at 1. And then my x-intercept was at 0, correct? Yes, my x-intercept was at 0. And then it went like this. It went above. So according to my table, to the left of 0, I'm above the x-axis. Then I go below the x-axis, and then I'm above. So this is what the graph looks like. And then at -2, there's a hole in the graph. So where that vertical asymptote normally appears, or I would expect it to appear, there is now just a hole. Okay? So when you're asked to determine when a hole happens, it's when when you have a factor that appears in the numerator and denominator that gets reduced, the vertical asymptote is replaced by a hole.